Welcome to the 24th class meeting of the Introduction to DSP. Last time I talked about not only the homework, but also the voluntary project. So if you have interest in getting an extra credit, then think about submitting your voluntary project. Here goes the overview. We are studying FFT, basically, the algorithm to efficiently compute the DFT. We've already seen the usefulness of discrete Fourier transform in many electrical engineering applications. And we will see something more, and you will see some other things more in your research. About here goes the correction. About the big O of n log n, computational complexity of FFT algorithms, I talked about the Taylor series expansion of the differentiation of log 1 x minus 1, but it turned out totally wrong. Forget about it, okay? So forget about what I mentioned about this log x minus 1. Okay, here goes the review. So last time, before we study the fast algorithms, we first checked the how many complex additions or complex multiplications are required to directly evaluate the DFT. So basically, what you need to remember is first the DTFT over signal, which is defined as the summation of xn times e to the negative j omega n, especially when xn is finite duration signal on n equals 0, ... up to capital N minus 1. And if you are interested in evaluating this DTFT over discrete time signal, at so-called Fourier DFT frequencies, which means that omega equals 2 pi divided by this n times k, then something good happens. So from the definition of DFT, you can easily see that the case DFT coefficient is nothing but the DTFT evaluated at the case DFT frequency. Got it? So this is what you need to remember. This one is general DTFT, and this is general DFT, especially when you view the vector x as a part of finite duration signal, then they have an interesting link. This will appear again and again and again. Excuse me. Now, what you need also to remember is that we need to compute this capital X of k for, in general, up to capital N minus 1. So if we find the number of complex additions and multiplications to compute just x of k, we need to multiply capital N. So without exploiting any property of W sub n defined as e to the negative j 2 pi divided by n, then as we see here in the summand of the summation, we need one complex multiplication n times. So n square complex multiplications, and these terms needs to be summed, so n minus 1 complex additions. Anyway, in terms of infinite asymptotics, the complexity becomes big O of n squared. Got it? By the way, about the big O and little o notations, especially big O notations, you will see some problems in the homework 24. Anyway, So this is the kind of so-called baseline complexity. What we are going to do is to reduce the computational complexity that needs to be less than this one. Got it? So we've seen up to here. By the way, when we compute each coefficient, capital X of k, we find something interesting related to W sub n raised to the power of kn, in the sense that first we have periodicity, which means that if we choose, am I right? Sorry about that. If we replace n with n plus capital N, then we have the same value, because W sub n, kn, W sub n, kn, and this one becomes 1. Got it? And we have symmetry, especially about the, for example, real part of kn and the real part of W sub n, k, capital N minus n. Because this W sub n is complex exponential function, which is cosine 2 pi divided by n minus j sine 2 pi divided by n. If we raised this to the power of kn, what happens? The real part, which is cosine, has period n, and also it becomes an even function. So they are the same. Got it? Similarly, we can find the kind of symmetry, odd symmetry, in the imaginary part of this W sub n kn. So by exploiting this periodicity and symmetry of W sub n raised to the power of kn, we can further reduce, even in the direct computation. However, even if we reduce the complexity into half, the problem is that big O of n squared is actually nothing but the big O of n squared divided by 2. So in this way, actually, we cannot get significant computation reduction when n is very large. Of course, we can say the complexity into half, but that is not significant. Got it? Anyway, in the past to the FFT algorithms, there was an algorithm which was quite interesting. And the algorithm's name is Goertzel algorithm, or Goertzel's algorithm. By the way, when you put the in the name, there shouldn't be apostrophe s, but if you remove this then Goertzel's algorithm. That kind of thing is very minor, but quite often students make mistakes when they write reports or papers. Anyway, what was the interesting part was actually in Goertzel's algorithm, they view this one somehow as what? As parallel capital N LTI systems. So we construct this discrete time signal x of n as a causal signal, so which means that the value is 0 before the time n equals 0, and it starts to become possibly non-zero up to capital N minus 1, and then again zeros. And here you have causal LTI filters. And interestingly, when you sample the output of the causal LTI filters at n equals capital N minus 1, n, N. Is it N? Yeah, N. Then actually you have the zeroth entry of the DFT up to the n-1th entry of the DFT. So what you need to remember is actually this one, as far as I'm concerned. So sometimes you need to view such a summation of the product as a convolution by multiplying some trivial term, trivial factor. Probably you remember what was the trivial factor. And then you rewrite, somehow manage this sample as the LTI filter output evaluated at specific time instant. And another interesting thing, what we've seen is that this LTI filter could be implemented by using a very few number of delay components and complex multipliers. So let's see the trick. So the first thing is that we could rewrite each LTI filter, so each LTI filter, as what? As first order autoregressive model, which means that we need the delayed version of the output and the output to link with the current input. And whenever we have such linear constant coefficient difference equation, we can find the system function in this form. Sorry. Got it? So here we have 1 minus W sub n raised to the power of negative k times Z inverse. So we may have this system for each branch in the bank of LTI filters. So Xin comes, and you have here delay component, and here goes your complex multiplier. And the kth branch has what? The kth constant. It's time invariant, as I claimed. It's linear constant coefficient. Constant for each kth branch. Got it? And you have the output named y sub k of n. And if it is sampled at capital N, it becomes what? X of k. See that? Got it? So be careful. Here goes many indices. First, this n is discrete time index. The k are the branch index. And here capital N is the sampling instant of the output. So here each branch has single complex multiplication and single complex addition, but because this is recursively generates the output, this single addition, single multiplication becomes n additions and n multiplications. And you may say that, what's the use of it? So basically, Goertzel's algorithm, which is interesting and gives us a lot of lessons, does not much reduce the complexity yet. But let's see anyway. Sometimes following the historical development of some path of the algorithms, we learn interesting things. So let's see. This one can be further manipulated by multiplying the same polynomial in Z inverse, which is reciprocal, which has reciprocal coefficients. So be careful. This one has the power negative k, and this 2 has positive k's, right? So we basically multiplied 1 to the original system function. But by combining these two factors, even though the order of the denominator becomes now 2, we have one benefit. What is that? We have real valued coefficient. And actually, this is quite often used in linear constant coefficient difference equation implementation. We really love real valued constant coefficient difference equation. And exactly that's what we are doing here. And of course, you may say that some insect is crawling here. Anyway, so you may say that in this era of fast computation, what's the difference between real multiplication and complex multiplication? Of course, you may say that if you have general purpose computer and use some programming language like the computational program like MATLAB, anyway, you write a simple code and it does everything. Sometimes when computation is intensively required, when you write an HDL code that really maps to an ASIC, you need to reduce the number of multiplications, even if it reduces into just a half, because that reduces a lot of, for example, heat dissipated by the system. And probably you know that these days, as the ASICs has narrower and narrower lines, then even though it requires very small current, because we have exponentially many transistors, the heat becomes the problem in many newly produced chips. So anyway, never forget that half of the computational burden removed is actually contributing a lot. Probably you have some ideas about the heat transfer if you have taken, since you have taken introductory physics or general physics in your freshman. When you have some heat generator, and that generates the or transfers the energy continually. If you have the temperature sink here, sometimes if you don't have enough balance, the temperature blows up. What does that mean? If the temperature blows up in your chip, it would be burnt down. So half of the complexity is actually very, very significant, even though our classical theory of complexity says big O of n squared is the same as big O of n squared divided by 2. So actually, whether it is significant or not really depends on the situation. Anyway, so here, this trick, now the difference is that before the numerator was 1, but now the numerator is not 1, but 1 minus some complex number and delay component. We may use so-called direct form 2 implementation. And we will see actually later in this course if you have time. But according to the order in the textbook, we should have seen this in the previous chapters. By the way, the terminology direct form 2, of course, there is direct form 1. You may have seen it in the signal gen systems. But the trick is simple. So last time I forgot about the index k, so I put subscript k's here to make it more precise. The idea is that when you have the output Z transform, you multiply the system function and input Z transform. What you do is that you first take care of the pole implementation. So you replace this one with a new discrete time sequence V, then the output now can be written in this way, which is that output is the FIR filtering of the intermediate signal V. So this way, the above single delay implementation can be implemented this way. So this IIR filter with a single delay component now can be implemented this way. And you may say that, hey, there are too many compared to single delay component. Delay components here, there, and there. What does this mean, by the way? Long before the memory of the system become less expensive, single delay component means single storage cell. And that was once very costly. Okay? You may not believe. So in that way, this looked very expensive. But if, here goes if complex multiplication that requires 4 real multiplications may save more if it turns into the single real multiplication, then it's okay. Got it? Of course, you may say that, well, professor, the DRAM-like random access memory requires or consumes energy every fraction of seconds to refresh itself. You are right, but usually when we have this small system, there was no expensive RAM with large size. But anyway, so here goes storage. One good thing is this one. As you remember here, what we need to do is to sample just once of this discrete time signal. Theoretically, this is an infinite length signal, but it should be causal because we assume causal system, a causal signal and causal systems. But since we sample once, actually, we don't need to store every V sub k of n for each time index n, right? We just need to store 2 of them, when Vk of capital N and Vk of capital N minus 1. And also this complex multiplication, here I forgot the negative sign last time, needs to be multiplied just once, not n times. Got it? So this way, anyway, we can reduce the computational complexity. And also, as we see in the explanation below, we can further reduce by, again, exploiting the periodicity and symmetry of the constant W sub n. That's what we are going to see. So let's see that first. So remember this structure to generate what? X of k. Oh. I don't, oh my God. Let me continue. So here, this is the case LTI system to compute capital X of k. By exploiting the symmetry, here we have cosine, so we can exploit the symmetry. We can reuse this part. We can reuse V sub k of n to generate capital X of n minus k. Because if you replace k with n minus k, this cosine is the same. Got it? And also, when we multiply this one, we can also at least reuse the sum of among 4 factors. By combining them, we can reduce the complexity. So this is the idea. So here goes xn. supposedly this is the AR2 for the case branch, but this output is not only used to generate capital X of K, but also to generate capital X of, sorry, why? Yeah. To generate capital X of N minus K. Got it? So we can reduce the complexity by exploiting the symmetry. However, as I repeatedly told you, still in terms of big O notation, we have complexity big O of n squared. By the way, here goes some good thing for this Goertzel's algorithm. Suppose we do not want to compute x of k for all k, but sum of k values. Here, sum means some capital M values. For example, first M of them. Every second terms. And M is very small compared to N. In that case, since each branch requires big O of N, then we have around big O of Mn complexity compared to big O of N log N. Sometimes M may be smaller than N log N. See that? Sorry. Other. Right? So this is the Goertzel's algorithm to compute only M DFT coefficient. And this is the FFT algorithm that just generates all coefficients. Sometimes M may be less than log N if M is sufficiently small and N is sufficiently large. In that case, why not using Goertzel's algorithm instead of FFT? So in that sense, still this algorithm is interesting. Got it? And another thing is this one. To have the right side, N log N complexity, we need basically, in general, we need N needs to be 2 raised to the power of some nu. However, Goertzel's algorithm can be modified to generate for any interesting coefficient. And here goes the idea. Suppose, so we start from this one. Suppose we have x of n time, x of n signal, discrete time signal, time limited or of finite duration. And you want to compute the DTFT at some omega sub a, which is not necessarily some DFT frequency. Got it? Then you can show that the pole part still becomes second order IIR filter. So you have output, 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 right? And here goes the input. And to sample, to generate the DTFT, you need to take the 2 values of the output, V, and similarly multiply e to the negative j omega sub a. And here goes some strange, not that intuitive constant vector. But anyway, again, you can keep almost the same structure as this one to compute the arbitrary DTFT, not necessarily a rational multiple of 2 pi divided by n. Sorry, the constant multiple of 2 pi over capital N. By the way, why do we have that one? So in order to understand why there should be that constant, let's go back to the original initial derivation in the Goertzel's algorithm. So you should start from here. And this is what? This is DTFT evaluated at e to the j 2 pi k divided by n. Now, instead of having 2 pi k divided by n, consider omega sub a. Then this one should be different. That's why you have non-unity here in the in front of this moving average part. Got it? So you do it yourself. Okay, you don't want to do it. Then I will try to remember and put that problem of proving equation 9.13b in the homework. Okay, that's good. So you've seen that Goertzel's algorithm still can find interesting applications, even though currently very fast algorithms, very large memory size, very fast systems are available. As I told you last time, Goertzel's algorithm not only has that interesting properties, but also has what? No small latency, just a single clock to generate the output. Of course, that can be negligible in this era. Okay, here goes the section 9.1.3, where the history toward FFT algorithms is summarized. They say that the computational algorithms to exploit the symmetry and periodicity of W sub n raised to the power of k n has been used even by Gauss, Friedrich Gauss. But around in 1965, even before I was born, Cooley and Tukey, it's usually read Tukey, published the algorithm to reduce the complexity, especially when n is a composite number, which means that n equals 2 times 5, something like that. And then a lot of research work has been done for 2 to the new. And here comes the family of fast algorithms called the fast Fourier transform algorithms. Now you know that this is fast discrete Fourier transform algorithms, even though this discrete, the word is gone somehow, right? Fast DFT algorithms. And this fast DFT algorithm is basically doing something like this. Suppose you have 2 to the 5, 32. Now it is divided by 16 and 16, and each one by 8 and 8, each one by 4 and 4, each one by 2 and 2. So what is the so-called depth here? Depth is simply log 2 base n, which is log 2 base 2 nu is nu, right? So this way we reduce the complexity. There are many versions of FFT algorithms. So suppose that this is the set of all, not still growing, all FFT algorithms. And majority of this one falls in the decimation in time and decimation in frequency FFT algorithms. And since we are not covering every specific algorithms, we will focus on decimation in time algorithms. Why this is called decimation in time? So I have decided just to show you the final form of the algorithm that is shown in page 32 of the slide. This is for when n equals 8. Ready? So we have length 8 vector x that has x0 up to x7 in the entries. And we have capital X vector that has capital X of 0, dot, 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 up to capital X of 7 as its entries. And as you see, of course, this can be rearranged. Here goes something interesting. You have here the first even indices. So here, n equals 0, 2, 4, 6, right? 0, 2, 4, 6. And in the lower branch, you have 1, 3, 5, 7. Got it? And as you see here, before you have final outputs, they are not interacting, right? So these x0, 0, 2, 4, 6 does not interact with the intermediate values up until the last stage here, right? And also, if you subdivide, this 0, 4 does not interact up until the second last stage. So now let's focus on up to here. Then what do you need? Actually, what you need to do is to obtain even part of x, which is what? Downsampling, decimation, downsample by a factor of 2. And here you need advance or delay if you want, and then downsample or decimation. Okay, so this type of FFT algorithm is called decimation in time. Now let's see another idea. Where it is? Okay, here. So as you see here, here goes x, and here left shift by 1 is kind of strange, right? What is left and right when you have a vector? But if you have a discrete time signal, then left shift means time advancing, not delaying, right? So you add 1. If you subtract 1, it's delay, right? So this is actually time advancing. Time advance. Got it? So here goes x, and you downsample to have x0, 2, 4, 6. And here, of course, previous ones, if you, to be precise, but anyway, we are not going to use it. And here goes downsampler. So we have odd components. And of course, let's cut the system here. And you can easily see that by reversing the downsampling, by upsampling by the factor of 2, and upsampling by factor of 2, and right shift to nullify this left shift. And then we add, what do we have? We have here G sub E that has something like this. So only at every even time instant, you may have non-zeros. And again here, every odd, but by right shifting, you have, here again, you have every even number index, you may have non-zero, but by right shifting, every odd number of n, you have non-zeros. And if you add them up, there is no non-zero two terms added, but you may reconstruct x. So here, this figure just shows visually that this down sampling by a factor of 2 and left shift component preserves the information. And there goes the idea of decimation in time. Okay? So no information loss by just rearranging them. And now, let's see how the complexity is reduced. So from here to here, what happens? What happens? What are these? W sub n raised to power of 0 is just 1, right? So actually, you are not doing any computation. Now, from here to here, what do? Again, 1 and negative 1 does not do much computation. You may say that it's multiplying negative 1, but as you learned in digital systems, there is a bit assigned to show that the number is positive and negative when you have finite bit assignments. So just flipping that bit, you can negate you can multiply negative 1, right? So this is none of the high computational complexity. We focus on complex multiplications only so far. Now, here, what happens? We have complex multiplications, but these are just 1 and these are non-unity. So we need some computation. Now, from here to there, still just complex additions. And here goes what? Here goes complex multiplications. And then we have additions. So this way, in the 8-point DFT, whenever we have single stage, single stage, single stage, we may just say that big O of n complex multiplications occur in each stage. And how many stages do we have in this case? 3. Now, in general, so from 1 to many idea, if we recursively extend this idea to some capital N that is equal to 2 to the nu, how many complex multiplications do we need in terms of big O notation? So each stage needs that one. And we have how many? Log 2 to the n stages. So that is n log n. Got it? So this is the idea. And we will see why this structure is obtained. By the way, you may not like this non-standard order, but you can just rearrange this one and to get this structure if you want, at least for the output. See that? Is it correct? Just a second. Something's not correct. Which? Yeah, okay. Okay. I'll talk it later. Anyway, so the first thing is to do single step. So here goes the idea. So from here, even though this is for discrete time signal processing, as I told you, by viewing our signal, the vector signal, to be transformed as the first capital N entries of a finite duration discrete time signal, we can link the DTFT of this signal X with the DFT of the vector, right? So this is the key. So our textbook explains how to obtain that FFT algorithm by focusing on how can we rewrite DTFT in this decimation in time procedure. See that? Instead of just doing computation for the DTFT of X, actually we can do nothing. We have some reversible system. So this is the inverse system of that one. So this operation is reversed. But by taking the intermediate signals, we can obtain something interesting. So let's focus on that one at the output. Now, the question is simple. So this is Fourier transformed. What does that mean? You need to Fourier transform this one. And you need to Fourier transform that one, which is the delayed version of capital H sub E of N. Any delay becomes what? Linear phase shift. And you have HE. I want this too big. E to the J omega. So you see the power of this reversible representation. Initially, it looks like a very stupid thing to do, to have something the same. However, this DTFT now can be rewritten as the DTFT of this part and the DTFT of the delayed version of that one. Like this, right? This is written in equation, the upper part of equation 9.15, right? So this is nothing but that one. Am I right? Now, when we studied upsampling and downsampling, we've seen the link between the DTFTs of the signals before and after the upsampling. What was that? I hope you remember. There are some analogies you've seen in signals and systems. Suppose you interpolate a discrete time signal X using interpolation function P to obtain some signal, continuous time signal. Then what is the Fourier transform, continuous time Fourier transform of this one in terms of the continuous time Fourier transform of this one and the discrete time Fourier transform of that one? You can show this is the answer. So here, P of T becomes capital P of F. It's quite natural, right? Because this is a linear combination of delayed version of P. So if there was no frequency component outside the bandwidth of P of T, the output should not have any signal component outside the bandwidth of P of T. So this factor makes sense. Now, for X of N, since this is a discrete time signal, you just have a discrete time Fourier transform, capital X of e to the j omega or e to the j 2 pi f. As a communication engineer, I love e to the j 2 pi f. But since you have interpolation period capital T, this signal needs to be adjusted, scaled by replacing f with ft. In one simplest case is when this P is direct delta. Then what happens? Delta of T has DTFT, CTFT, or one function. So you just don't have that one. So now you remember that after interpolation, you have original DTFT scaled by the period. Right? Same thing happens when you do upsampling. Upsampling by a factor of L can be written this way. So here is your input signal X to be upsampled by a factor of L, which means that you plug in capital L minus zeros between two consecutive samples. Then similar to that one, you have this one. So DTFT of this signal now has omega replaced by omega times L, or 2 pi f replaced by 2 pi fl. So we've seen this guy appears here first. Now, what did I tell you? Before and after upsampling, our DTFTs are linked what? So here you see that the input is what? The input is we named G. So G of n is upsampled by a factor of 2. Then my question is, what is the relation between the DTFT of G of n and the DTFT of G sub E of n? We want to replace this one now with DTFT of that one. What would be? G, capital G of e to the j omega times 2, because we have a factor 2. So we have this one. Ready? Be careful. We have subscript E in the first line, and we don't have subscript E, because this capital G is before the upsampling by 2. And this G sub E is after upsampling. Similarly, this one with H sub E now can be replaced by that. In the same reason, see that? You see? This is H. And after upsampling, you have H sub E. Got it? Now, we are almost done. We need to handle these signals. So here goes the question. What is the relation in the frequency domain? Which means that what are the relation among DTFTs of this signal and that signal, and this signal and that signal after downsampling? Downsampling is more like sampling over a continuous time signal uniformly, where we have spectrum folding, right, and some scaling. And in the similar reason, you can show this. So this G here, this is after downsampling, can be linked with DTFT of the input to the downsampler this way. And this H also before you replace by 2 omega, like this one. So here, finally, you need to replace omega with 2 omega, omega with 2 omega, and plug in here. Then you have what? DTFT of the original signal in terms of the DTFTs of the decimated signals. Got it? And that is written here. Okay? So I kind of explained the number reversed order of the equations. So as I told you, the case DFT coefficient is simply the DTFT of the signal evaluated at 2 pi k divided by n. Now we have general formula for the DTFT with omega here. What is that? G of e to the j omega times 2 plus e to the negative j omega h of e to the j omega times 2, as we've seen here. Where it is. Yeah. Ready? Now, let's take a more in-depth look at the first term and the second factor of the second term in terms of x. So this one is what? This one is DTFT of G evaluated at that frequency omega. So simply, this is the definition. And now you see that the even part of x is only taken. Now, you can move this 2 to the denominator. What does that mean? Actually, you are equating these two. W sub n, which is e to the j2 pi divided by n raised to the power of 2kn, is the same as e to the j2 pi divided by n over 2 raised to the power of kn, right? They are the same. Now, what is this interpretation? This is what? This is DFT. Now, this is DFT with capital N over 2 point. Similarly, the second factor of the second term can be viewed as what? The odd part vector, DFT, with number of points capital N over 2. So here comes the final form. The case DFT coefficient is what? The summation of the case coefficient of the n over 2 point DFT of the even part plus a constant which is related to this k times the other part's DFT. Now the authors developed a notation that is quite strange, this double parenthesis. But since this equation must hold for all capital N, and we need to define G of double parenthesis k sub n over 2 by periodically extending the n point 2 point n divided by 2 point DFTs. So GK is of length what? N over 2, right? Because G of K is the even parts DFT. So let's see. X is what? Complex length n. X even is complex length n over 2. But here, if we view as this capital X and this as capital G, something is wrong, right? Capital G is what? Just length half of the n. So we periodically extend and show that this holds. Same for the second factor of the second term. Now, this is quite confusing. This is the way to view the equation. So here goes the signal flow graph. Just for the division into two branches, even and odd, just one, not yet complete. So here goes your original signal. You take the even terms to generate a smaller size vector. And you take the odd terms to generate smaller size vector. And now you do smaller size, half-size the DFTs. And here goes G1 through G3 because the output is of length n/2. Here you have H0 to H3. Now let's focus on only the outputs capital X to X3. What do you have? According to the previous formula, this vector and that vector added after this vector properly scaled by these coefficients, right? Before it is added, it is multiplied by this vector. And these coefficients are different for these four entries. Now, for the second half, again, you have G vector copied because its periodic extension satisfies the formula. And when this H part goes there, as you see, you have complex number multiplied. Got it? So basically, this shows how decimation in time can convert n-point DFT into 2 n/2 point DFTs with some extra scaling and addition. And this part can also be simplified. So let's see. Suppose we do the previous idea again and again. So far, this part is this part. Yeah. This part is same as this one. And same as this one, right? See that? They are the same, right? So what you need to do is to convert each n/2 point DFT into 2 n/4 point DFTs. And by just copying the idea, you can have this one. Sorry. Now, each 4 input DFTs needs two output DFTs. So far, it's not that obvious that we have really reduced the complexity, computational complexity to n complex multiplications per stage. It's not yet, because you see that, hey, n, 2n, really? But here goes another idea. So if you take a look at each 2 of the signals, see that? You have something like this. Is it 4? Yeah. And if you just focus on this one, sorry, not this one. Let's focus on this. That is related to these two and that one. So we only consider these 4 branches, and it has almost the same structure. So we focus on this one more in depth to have this idea. So this is the m-1 stage, and this is m stage, and we have something like this, always. And let's focus on these 2 coefficients. Apparently, from here to that one, 2 input to 2 outputs, we need 2 complex multiplications. And the question is that really required? And we focus on this part. What is this one? And this one is -1. And as I told you, multiplying -1 is just negating one of the bits. So this becomes that. Can you see? This one is factored out because they are common. So from here, you have 2 complex numbers to be multiplied, but instead, you multiply this one first. So here, you multiply this one first. And here you just add, here you just subtract. Got it? So each branch now becomes what? Scaling, single complex multiplication, and addition or subtraction, which is just addition. That's why you have this one. Got it? For 8-point DFT. So let's talk about generalization from 8-point to general endpoint, as shown here. So by repeating this one, the idea can be generalized to any 2 to the new, any n that is 2 to the new. And as you see that, each stage requires big O of n complex multiplications. And you have how many? Log n, which is log 2 to the 2 new stages. So you have big O of n log n. Got it? And they say that some special hardware can be used for with a better algorithm, and that's not the topic of this course, but you should remember. Anyway, this is the principle, basic idea in FFT. You can have a lot of variations depending on what kind of signal you are handling. For example, suppose your signal X is real valued, not general complex valued. There are some times you need to perform FFT on real valued vector. Then can you save some computational burden? Yes, you can. What if X is symmetrical, which means that the first and last is the same, second and second last is the same, third last, something like that. In that case, you can save some computation time. And even what you can do is that if you need to make an ASIC, then your HDL code can be much simplified and save a lot of energy and time to efficiently do the FFT. Anyway, so what I want to say is that there are many variations and much of the details to be taken care of when you really implement this one in AC. Even the textbook talks about how to assign each xn and xk into some order. For example, as you see here, let's see here. Say that here you have 0, 4, 2, 6, 1. Is it confusing why we don't have the 0, 1, 2, 3, 4, 5, 6, 7, something like that? So this kind of shuffling can be complicated in the design of some circuits. So when symmetry in the circuit is required, they say that the order can be somehow generalized this way, like this. They say that this structure, which is equivalent, exactly the same as that one, can be more suitable for some implementation. Got it? So that's what you need to remember. Now, we have around 3 or 5 minutes. So let's see decimation in frequency FT algorithm very quickly. And it'll take just 3 minutes. So due to the symmetry in the analysis equation and synthesis equation of DFT, right? We can just consider decimation in frequency as we've done in decimation in time. So here goes the idea. Suppose we have discrete time signal that is of finite duration. So from capital X of 0 to capital X of capital N minus 1, then we have possibly non-zero and all 0 signals. And here goes, this could be circular shift. But anyway, here decimation in frequency domain. And as we've seen, the output is the same as the input. Now, what do? We again use the property of the upsampler and downsampler related to the DTFT. And this is what we can do. So first, we just divide the output, right, into even and odd samples. And here goes the idea. We can now utilize 2 capital N over 2 point DFTs. And this part is what? Just complex addition and differentiation. And here goes the complex multiplications. Then we do it again for this one. Again and again and again. Eventually, we have this. So this is decimation in frequency 8-point FFT. And this can be repeated again and again. And even the input can be rearranged. See that here from 0 to 7. And 1, 0, 1, 2, 3. So it can be rearranged this way. So you have x0 to x7. They are the same. Got it? And of course, you can rearrange this part to have this result. So basically, decimation in time algorithm, if you understand, decimation in frequency FFT algorithm can be understood with some energy and time spent on that. Not that difficult. Got it? And here goes the, do I need to cover it? I will try. Section 9.4, and the authors of the textbook talks more about the details when it is used to really implement some system. So
Joe. It is
Yeah.
time to wrap up.
Okay.
Doctor.
We'll do it later in the next week. Okay, so I will assume that we have covered up to section 9.3, and we'll give you the homework. Okay, that's all for the day.